Severe climate-induced droughts are shrinking traditional freshwater reservoirs. To compensate, nations are building new industrial-scale water sources from the ground up. Governments are investing in seawater and brackish water desalination infrastructure to secure water for populations, agriculture, and industry. This chart shows the surge in Europe's cumulative seawater desalination capacity over the last few decades. But that water production curve hides a parallel surge in electrical demand. Generating fresh water requires immense amounts of continuous power. Solving the physical water shortage creates a new, massive variable within the electrical grid. Inside a modern desalination facility, the engineering focus shifts from water production to massive electrical consumption. Historically, standard plants rely on 100% asynchronous induction motors. These are highly predictable, heavy rotating machines. Today, modern plants use hybrid systems, layering power electronics over core mechanical operations to gain efficiency and operational control. Combining these massive power electronic loads with intermittent renewable energy changes the system strength of the grid. System strength is a metric that defines how well a power grid can maintain stable voltage and frequency during disturbances. Integrating these mega facilities into the network forces the requirements of water security and power system stability into a single complex engineering problem. Reverse osmosis, or RO, is the most common method of modern desalination. It is also the most energy-intensive process. This schematic shows a reverse osmosis membrane. Forcing seawater through these microscopic barriers requires immense pressure from direct-coupled asynchronous induction motors, consistently drawing 3 to 6 kilowatt-hours per cubic meter. Because a reverse osmosis plant must operate continuously to meet a city's water needs, it forms an unyielding, heavy load on the local distribution network. Spain suffers from severe chronic water shortages, with some regional reservoirs dropping below 16% capacity. To address this, the country has built 770 desalination plants, making it the 5th largest producer of desalinated water in the world. Consider the dense Mediterranean coastal city of Alicante. This map shows the Alicante region. The city consumes roughly 200,000 cubic meters of desalinated water every day. Based on our reverse osmosis metrics, that municipal demand requires up to 800,000 kilowatt-hours of electricity daily. That localized, concentrated power draw equals the daily energy use of thousands of residential households concentrated in a single industrial footprint. When this load runs during peak electricity demand hours, it requires grid operators to deploy dedicated generation capacity or aggressive load balancing to prevent local failures. A single municipal desalination plant acts as a geographic megawatt sink, shifting regional transmission flows and creating specific localized grid stress patterns. The traditional setup of asynchronous induction motors provided a crucial benefit to the electrical network: high rotational inertia. That spinning physical mass inherently resists sudden changes in power flow, keeping the grid stable. To improve flexibility, engineers are shifting toward variable frequency drives, or VFDs. These power electronic devices control a motor's speed by actively changing the frequency and voltage of the supplied electricity. This block diagram shows the hybrid architecture. The alternating current from the grid now passes through a power electronics layer before it reaches the mechanical asynchronous motors. This layer allows operators to dynamically control pump speeds, optimizing water flow and integrating with variable power sources. The facility's mechanical efficiency improves, but its electrical signature loses the predictable, heavy physical properties that traditionally anchored the grid. By optimizing the facility strictly to produce water efficiently, engineers strip away the electromechanical stabilizing force the local transmission network relied on. Powering an 800,000 kilowatt-hour daily facility with conventional thermal plants running on fossil fuels creates a significant carbon footprint. The industry's response is to pair major desalination projects with renewable energy sources, or RES. Massive solar arrays are deployed to offset the heavy daytime energy demands of the reverse osmosis cycle. Here is the engineering catch. Wind and solar generation do not possess heavy physical rotating mass. They interface with the grid entirely through power electronic inverters. To solve the carbon emissions problem, we are replacing heavy, stable, synchronous generation with the same inverter-based technology that complicates the desalination load. This animation compares the physics of the two setups. On the left is the traditional grid, where heavy rotating turbines power direct induction motors. On the right is the modern grid, solar and wind inverters pushing power to desalination variable frequency drives. Watch what happens during a transient fault, like a lightning strike. On the left side, the physical momentum of the heavy rotors keeps them spinning. They resist the change, holding the alternating current sine wave steady. On the right side, the modern grid suffers from a reduction in system strength. Without spinning momentum to absorb the shock, the exact same fault causes the alternating current sine waves to immediately distort and swing out of phase. Without intervention, this delicate new configuration leads to unpredictable electrical instabilities and an increased risk of severe regional blackouts. Transmission system operators, the entities responsible for grid stability, are caught in a difficult position. Upgrading physical transmission lines takes years, but the demand for water is immediate. As a first line of defense, TSOs are mandating strict technical robustness requirements. They now require accurate dynamic models from plant manufacturers to assess risks before allowing grid interconnection. The technological fix relies on grid-forming technologies. This diagram shows a grid-forming inverter placed at the desalination plant boundary. It actively generates a rigid alternating current sine wave, forcing the erratic local grid voltage to synchronize to its rhythm. Unlike older inverters that passively follow the grid, grid-forming inverters artificially inject the missing inertia, actively propping up the local system strength through high-speed software controls. Preventing a thirsty world from causing a regional blackout relies on mastering these advanced controls. We have to synthetically recreate the physical stability of the past to safely run the critical infrastructure of the future.